Thanks a lot. My name is Peter Blouw. I'm a research scientist at Applied Brain Research. We're a software company based out of Waterloo, and we're working on commercializing neuromorphic technologies. And today I'm going to talk about some work I've done with my colleagues on profiling the performance characteristics of Intel's Blouw research chip in the context of a keyword spotting task. So this is a standard speech recognition task that is in pretty much every cell phone. So you're likely very familiar with it. To start with some high-level motivation, this has come up already, but when we look at neuromorphic hardware, there's sort of two key features that are likely to bring performance benefits. One is architectural parallelism, and the other is an event-driven model of computation. So with event-driven computing, you only spend power on compute when certain signals of interest are provided in your input. So that results in temporal sparsity, which can improve energy efficiency. And then having architectural parallelism can improve latency because you have fewer sequential steps between transforming an input into an output. And in the context of deep learning style inference tasks, it's worth wondering how much of a benefit can we get from implementing these tasks on a neuromorphic computer. And Intel's chip is a great tool for analyzing these benefits, specifically in the context of speech recognition like we're doing here. So we have software at ABR that we've developed that will allow you to take an arbitrary deep feed-forward neural network and translate that into an equivalent spiking neural network that has approximately the same performance characteristics. So we can just take that deep network, turn it into a spiking network, and then run it on the chip. And then once we've done that, we can compare a bunch of performance characteristics of that spiking neural network to equivalent deep networks running on more conventional hardware devices. So to get into some of the specifics, what we're really interested in here is performing controlled experiments on hardware devices. So our independent variables are going to be things like different chips, and our dependent variables are going to be metrics like inference speed, dynamic power consumption, and energy cost per inference. So we'd like to take a rigorous quantitative approach to doing this benchmarking. And the specific task that we're looking at is keyword spotting. So this is what your cell phone does when you say, OK, Google, or Hey, Siri, to activate the phone. So you're monitoring an audio signal continuously for a specific keyword. Here, we're looking for the target phrase aloha. And we're going to use a simple two-layer feed-forward neural network to do that. In terms of metrics, what we're interested in are basically three numbers. So inference speed, so how many inferences per second can you perform with this neural network? Dynamic power consumption, so how much energy are you spending to get that many inferences per second? And then energy cost per inference. And that's basically how many joules does it cost you to perform one inference with this neural network. And that actually just follows from the first two numbers. And then we can measure these quantities on different devices running the same network, the same number of parameters on the same input data. So the only thing that's really changing is the hardware. And we'll look at 5 devices, so a standard Xeon CPU, a NVIDIA GPU, the NVIDIA Jetson, which is a low-power GPU, the NVIDIA Neural Compute Stick, which is specific inference-only low-power deep learning chipset, and then the Blouw research chip. And one thing to note here is that the comparison is between research and production devices. So that's just something to keep in mind when evaluating these results. OK, so to start out with some of the highlights. So as I said already, it's a simple two-layer neural network architecture. So the input is a 390-dimensional feature vector derived from a speech signal. I'll talk a little bit more about how we get that. Then we have two 256-dimensional hidden layers, and then we read out a 29-dimensional vector that is a probability distribution over alphabetical characters. We get a stream of characters. If they line up with a particular keyword, we spit out a positive classification judgment. Otherwise, it's a negative classification judgment. So to train a spiking neural network to run on Blouw, we use a software package from ABR called ZangoDL. And that lets us take this network architecture, train it to run in spiking mode, and then we can port it onto the chip. And then on every other hardware device, we're just going to use TensorFlow to train this model architecture in the standard way that you would train any deep network in TensorFlow. And then we can run the identical model with identical parameters on all of the hardware devices. And what this graph is showing here is the energy cost per inference on all of these hardware devices expressed as a ratio. So one inference here is one forward pass through the network. So putting in a feature vector and then reading out a distribution over characters. And if we take Blouw as a baseline, we see these are slightly updated results from the results you saw earlier in Mike's talk. But we're seeing that it costs 5 times as much energy, roughly, to do one forward pass through this network on the closest alternative device, which is the Movidius neural compute stick. So this is really exciting from our perspective because it's showing that for deep learning style inference tasks, we can actually get a good performance boost by using a neuromorphic computer. And then if we go to other devices, we see even greater increases in energy costs. So we're in the realm of 20x for things like the Jetson or a standard CPU, and then over 100x for a GPU. And again, this is batch size 1, so this is sort of a real-time inference task, which unsurprisingly, this would not be something that you would use a GPU for. So these big numbers over here shouldn't be particularly surprising in that context. OK, so that's just the highlights. A natural question to ask next is, what sort of performance cost are you getting by switching over to the spiking neural network? And these are, again, some slightly updated results. But the answer is it's very marginal. So we're actually doing a little bit better after some software updates on Dingo Luihi, but I wouldn't read too much into that just because it's such a small data set where 1 or 2% is just a handful of misclassifications on the test set. But what we're really showing here is you're getting performance parity more or less when you're comparing the spiking neural network to the standard deep network. In general, on more large-scale tasks, you will see a slight performance loss by switching over to the spiking network, but it's fairly minimal. So the key takeaway is we're getting near equivalent performance characteristics despite using a spiking network in place of a deep network. And then just a quick word about the data set. So this is a data set that we collected about a year ago for some demos. We got a bunch of people on Mechanical Turk to use their home computers to record themselves saying particular phrases. So we got about 2,000 training utterances split in a roughly 3-to-1 ratio between positive examples of our target phrase, aloha, and then we also collect negative examples of close distractor phrases. So these would be phrases like take a load off that are phonetically fairly similar. So they might be natural examples of false positives that we would want our model to avoid. And then for each speaker, we hold out 2 test utterances, 1 positive and 1 negative. So this is a relatively small data set, but again, the interest that we have here is not so much with model performance, although we do care about that. We're really looking at energy benchmarking. OK, so just to give you a quick overview of how the speech recognition system actually works. So you have some speech waveform. This is your input signal. And we're going to do a sliding window that we pass over that speech signal. And for each window, we want to map that to a specific alphabetical character. And with that window of audio, we'll do a standard feature preprocessing step that basically takes a Fourier transform and does some reweighting to give what's called a Mel frequency cepstral coefficient. And that's kind of a front-end thing that most speech preprocessing systems make use of. So what we have here is some inputs in the form of windowed audio features and some outputs in the form of alphabetical characters. And we want to use our neural network as a function approximator to approximate some function that maps from these windowed inputs to these target outputs. And then as we slide an audio signal, our window over this audio signal, we're going to spit out a bunch of character predictions using our neural network. And then we'll collapse down repeated characters and strip out blank symbols to produce a final text transcription. And then if that text transcription matches the keyword, we'll treat that as a positive classification. And otherwise, we'll treat that as a negative classification. So framed as such, this is just sort of a standard supervised machine learning task. So you have your feature inputs and your target outputs. And you can take those inputs and outputs and train a standard ANN in TensorFlow. And that's what we do for all of the experiments that are run on conventional hardware devices. And then in the case of the Luihi experiments, we're actually going to do something somewhat similar, where we train a standard deep network, assuming a rate model that is a differentiable approximation to a leaky integrate and fire neurons tuning curve. And then once we've trained that rate model, we have a toolkit called NengoDL that will let you swap in a spiking version of that leaky integrate and fire neuron. And if you present an input over time, the filtered spike trains that are generated by those neuron models will converge on the rate values that the training method assumes. So I'm not going to talk a lot about that methodology, but I'll have a link at the end that will tell you a little bit more about the software package, and I can point you to papers if you want to talk to me afterwards. So this is just sort of the pipeline that we go through to map from our data to our implementation on these different hardware devices. So that gives you an overview of the model itself. Now in terms of the benchmarking methodology, there's basically 5 steps here. So the first thing we want to do is estimate idle power consumption on every device, so that we're not counting that in our measurements of dynamic power. So here we basically just take a time series of readings over a long period of time while the device is doing nothing, and we just average over that so that we're washing out anything that occurs due to intermittent OS processes on a CPU, for example. And then during our experiments, where we're just taking our model and pumping speech data through it as quickly as possible, we're going to log power readings at a fixed interval. It's typically 200 milliseconds in the case where we have software tools for logging power. So that gives us a time series of running power consumption. And then we can estimate dynamic power by subtracting out the idle baseline. And that gives us a time series of power readings that estimate the compute over each interval that is being allocated specifically to computation on our task of interest. And then we can also calculate the logging interval and the number of inferences per interval, because we can keep track of how long we ran the experiment for and how much data we actually pumped through the network, so how many inferences we performed. So if we have the amount of power spent per time interval and the number of inferences, we can calculate the energy cost per inference, which is really the metric that we're interested in. And we just use standard power benchmarking tools to do this. So NVIDIA SMI for the GPUs, and we have power meters for non-GPU and CPU devices. OK, so these are kind of the results that we get from that. And these are idle numbers on average, running numbers. And then these two numbers are really the things to care about, because dynamic power is power allocated to computation. And then inference speed is telling you how much compute you're getting for that power. And then joules per inference is really the number that we care about again. And that's telling you how much energy you're spending to do a forward pass through this neural network. So joules per second, that's our dynamic power. Inference per second, divide the latter by the former, and you get joules per inference. One thing to note here is that we've adopted a very conservative methodology. So in any case where there's like a question mark about what we should be treating as idle power or runtime power across the different devices, we've always made the assumption that's most generous to the conventional hardware systems. And we just did that to sort of allay skepticism about these results, and to make sure we have sort of like rock solid ground to stand on in terms of our confidence in the benchmarking that we're doing. And again, note this is all for batch size equals 1. Oh. There we go. OK, so just to repeat, this is our kind of key result for batch size equals 1 inference. So we're seeing very competitive results from a neuromorphic implementation of a standard deep network. And intuitively, you might not necessarily expect this to be the case, because with a standard deep network, all you have to do is encode your activation vector as a single floating point number, whereas if you're doing a spike-based implementation, you have to generate a bunch of spikes to approximate the rate that is encoded as that floating point number. So you're actually sort of forcing computation to occur over time in a way that might lead you to believe that it would be less efficient. But what we're showing here quite convincingly is that the temporal sparsity that you get out of a spiking network compensates for that to give you an overall reduction in power consumption. So that's quite nice. So just looking at the GPU, as I mentioned before, this is not an ideal use case for a GPU. So we can also look at what benefits you get from batching. So when you start batching data together, instead of just passing a vector corresponding to a single example through your network, you're actually going to stack a bunch of examples into a matrix. So all your matrix vector products become matrix-matrix products. And that can drastically improve your inference speed. So going up to a batch size of 64, you have a massive increase in inference speed across all of these devices. And correspondingly, that also drastically reduces the energy cost per inference. So what this is really telling you is that there's a lot of energy spent on the overhead of transferring data on and off a GPU and just managing that process. So the larger your batch size, the greater degree to which you minimize that cost relative to the amount of energy you're spending on compute. These lines here are showing you where batching becomes competitive with the energy cost per inference of Movidius and Blouw, which can't do batching. So they're only batch size equals 1 devices. But in the case of Blouw here, you need to be at a batch size of 64 or higher, basically, to be getting comparable energy performance on an energy cost per inference basis. So that's quite interesting. A further thing that we can look at is scaling the network internally while holding I/O fixed. So what this lets us do is isolate the relative contributions of energy spent on I/O versus energy spent on compute. And that lets us see how energy consumption scales as a function of network size. So if we take our original network that has just 2 layers, we can add in internal branches while keeping the input data constant across these different sizes of scaled network. So in this case, we'll add a 10-layer branch between these 2 hidden layers, and we'll have n of those branches. And that lets us scale the number of neurons in our network linearly and equivalently across all devices. So in the case where n equals 0, we have 512 neurons in the network. And in the case where n equals 10, we have about 26,000 neurons. So we're increasing the number of neurons by a factor of 50x as we sweep over this parameter n. And one thing to note here is that the scaled network is randomly parameterized because this is a huge network, and it's not really feasible or useful to train for a keyword spotting task. It's just way too many parameters. You'd overfit your data. So we're using a fixed distribution of weights that's the same across all devices. And it does generate spikes throughout the entire network. So we're not just introducing fake sparsity, for example, by having negative weights everywhere. All right. So if we look at the average dynamic power and inference speed on Blouw across these different values of n while we scale up the network, we do see, as expected, a monotonic increase of dynamic energy consumption and a corresponding dynamic monotonic increase in average energy cost per inference. We see a relatively flat inference speed. And this is quite encouraging because as we increase the number of neurons, we're actually seeing a fairly small marginal cost in terms of power for the additional compute that you get by having a much more complicated network. And to put these numbers in context, I can show you a comparison with Movidius. So if we do the equivalent scaling on Movidius, we have a much steeper sort of gradient in terms of the change in power consumption as a function of network size. And if we look at how the benefits of switching to the neuromorphic implementation increase as a function of network size, we see that we're just getting better and better results as the network gets larger and larger. And that's basically just saying that if your slope is a lot smaller, you're going to get a wider gap as you move out along this x-axis. So we have about a 2x difference in power consumption down here, and we're going up to about a 10x power difference over here. And another key feature is that inference speed is pretty much flat here, in contrast to Movidius, where as you scale up to these very large network sizes, you're actually going to be unable to perform real-time inference because your inference speed is going to be slower than real-time. So again, another advantage of neuromorphic implementation in this context. So I think if you only take away one slide from the whole talk, this should probably be the one, because I think this shows a lot of promise for the type of work that we're doing here in terms of a practical application of neuromorphic computing in the context of a real-world task that is commercially deployed right now. And we're sort of meeting the state of the art in terms of energy consumption. All right. So just to wrap up with some discussion points, scaling, again, this is sort of the key takeaway. So inference speed and average dynamic power consumption change very, very slowly with scaling on Blouw. And this is kind of the 2 things that I highlighted at the beginning of the talk at work. So you have architectural parallelism and event-driven computing. And those can really pay off. That's kind of the lesson that this experiment has taught us, I think. Another thing to note is that if you look at that previous slide where we're looking at inference speed, it's pretty much flat across all the different network sizes. And despite some optimizations to I/O, we're still basically bottlenecked by I/O. So we can only run the network as fast as we can pump data into it, which means that if we have further improvements on that front, we can likely shrink our cost per inference even more to some extent. And as a corollary, it doesn't look like spike trafficking is really the main source of energy consumption in a lot of these experiments. Again, it's important to note that comparison is between research and production devices. So there's lots of room for further analysis and benchmarking in the context of other applications. And finally, the methods that we're looking at here, they generalize to arbitrary deep networks. So there's nothing specific to automatic speech recognition. We can do the same thing with CompNet for doing MNIST or CFAR10. Basically, any feed-forward deep network you can think of, we can map into a spiking network using our software. So as a result, I think there are plenty of reasons to be optimistic about chips like Blouw as a platform for low-power deep learning. So with that, I'll just give you some pointers to software that we use to run these experiments. So NengoDL, that's what will let you translate a deep network into equivalent spiking network. And then NengoLuihi will let you define arbitrary spiking neural networks in a fairly simple high-level API that you can then port onto the chip itself. So with that, I'll just highlight my collaborators who worked on this project with me. So Sean Chu did a lot of the power benchmarking experiments. Eric actually put together the implementation of the network that ran on Blouw, and then Chris Elias-Smith is sort of the head of our group and oversaw and guided the research at a high level. So with that, thanks very much for listening. I don't know if there's time for questions, but I'm happy to talk to anyone who wants to learn more.
Thank you, Peter. I think we have time for one question.
Thanks for a good talk, Peter. You're talking about dynamic power.
Yeah.
And my question is about static power, because one of the trade-offs you make to get your parallelism is to have more silicon area, whereas Movidius is using less silicon area. So are you taking a hit in static power?
We haven't really looked at that. So I mean, so we're basically just treating the chip more or less as a black box where, this is the idle power consumption, this is the dynamic power consumption while you're running the application. What's the difference between the two? So if there is power cost in that sense, yeah.
You have the idle power.
Yeah, we do have the idle power, so we've definitely measured that. But is that what you mean by static power?
How much the idle power costing you?
Oh, yeah, so that, so I had the,
No, okay.
Yeah,
Yeah.
Movidius has a DRAM as well, remember?
Okay, I was just wondering about that.
yeah, sure.
So you can add additional questions at the break, which will happen soon after one small announcement. So let's thank Peter again.